All right. We're on chapter 14, page 512. All right. Let's look at number 2. It says, in the aftermath of an intense earthquake, the earth as a whole rings with a period of 54 minutes. All right. We're number 2, and we're on page 512. And so it rings, it rings with a period of 54 minutes. Okay. What is the frequency in hertz of this oscillation? Okay, so it rings or it oscillates with a period of 54 minutes. Well, this is really easy. If you remember your lecture, we know that the frequency is equal to 1 over the period, isn't it? So we say 1 over 54 minutes, but now wait a minute. We can't leave it in minutes, can we? No, we cannot. So we got to change that to seconds, don't we? Well, how many seconds are in 54 minutes? Well, it'd be 54 times 60, would it not? Because there's 60 seconds for every minute. So we get what? 1 over 3,240 seconds. And then we take the reciprocal of that. And we get a frequency of 3.08 times 10 to the negative 4th hertz, or reciprocal seconds, or we could just say 3.1 hertz. All right? Oh, well, wait a minute. 3.1 times 10 to the negative 4th hertz. Okay? All right. Okay? All right. Easy problem. Real easy problem. Okay. Next problem. Let's look at number 7. Man, this just don't want to work. All right, an air track glider is attached to a spring. The glider is pulled to the right and released from rest at time 0 seconds. All right. We're looking at number 7. Yeah. Okay. All right, so we got a, what is it now, an air track glider. So here's your track. You got a glider on here. There's the wing. Okay. And it's attached to a spring. Okay. And the glider's pulled to the right. Okay, so we pull it to the right. And released at time 0. So at time 0 seconds, it's released. Okay. It then oscillates with a period of 2 seconds. So it goes back and forth. And the period is 2 seconds. So it oscillates with a period of 2 seconds. And a maximum speed, and the velocity max is 40 centimeters per second. Okay. What is the amplitude of the oscillation? Okay, that's part A. And then we do what? What is the amplitude of the oscillation? So let's do that. Okay, so let's do A. Now you say, where are we going to get this? This actually comes from, we take the derivative, and I know we're not doing derivatives in here, but I'm going to show you where it comes from. The derivative of this equation right here, the displacement with respect to time is equal to A cosine of 2 pi over the period. Okay. X with respect to time is equal to A cosine 2 pi t, excuse me, I left my t off. Two pi t with respect to the period. Okay, so if we take the derivative of that, and by the way, when you take the derivative of cosine, you get what? Sine. All right, so that's going to be what? Well, that becomes this equation right here. V max is equal to 2 pi times A over T. 2 2 pi a over t. 2 pi a, which is the amplitude, over t. Oh, and by the way, did it give us the amplitude? No, that's what we're calculating. Okay? So we got to find what the amplitude is. So amplitude is equal to, well, we just solved for amplitude, y'all. That would be the velocity max times the period divided by what? 2 pi. And so the velocity max was 40 centimeters per second. Now we got to convert that to meters per second, so move the decimal 2 places to the left, so it'll be 0.4 meters per second times the period, which was 2 seconds, divided by 2 pi. And so what do we get? All right, well, we've got 0.4 times 2 divided by 2 made a mistake. Hang on. Been a long day. And we get 0.127 centimeters, or excuse me, meters. Which would be how many centimeters? Well, that would actually be what? If it's 0.12 meters, it'd be 12.7 centimeters, wouldn't it? Or 12.7 centimeters, right? Okay. All right. Now, you could round that up to 0.13 too. Now, part B says what? It says, what is the glider's position at 0.25 seconds? So we want to know what x is at time 0.25 seconds, question mark, right? All right, you say, well, how in the world are we going to find that? Okay, we're going to use this equation right here I just wrote. So we're going to say then x with respect to 0.25 seconds is equal to, the amplitude is 0.127 meters times cosine of 2 pi, and the time interval is 0.25 seconds. Okay, see, there's t right there. Divided by 2 seconds. Now all that's in parentheses. And so what do we get? Well, let's see. Let's do what's in parentheses first. Let's do our argument first. And so we get 2 times pi times 0.25, okay, divided by 2, and then take the cosine of that, times 0.127, and we get a time and I did it backwards, my bad. Okay, so let's do this again. So we've got 2 times pi times 0.25 divided by 2. And this answer right here, so we get what? We get 0.127 cosine of this right here, 0.78. Okay. Oh, I've got to put it in radians. Doggone it. I forgot. That's got to be in radian mode. Woo! Almost messed up. So you got to make sure you put your calculator in radian mode. Okay, so let me see if I can remember how to put it in radian mode. Don't remember how to do it. There we go. 2. Now, there we go. Now we're in radian mode. Okay. So we got 0.127 times cosine of 0.78. And we get 0.09. So we get 0.09 meters or 9 centimeters. Well, almost messed up on that one. You see what I did there now? You've got to, anytime you take the cosine of pi or something in radians, the cosine of an angle in radians, you've got to put your calculator in radian mode, okay? So make sure you know how to do that, okay? I had to dink around a little bit. It's been a while since I've used this calculator, okay? So 9 centimeters or 0.09 meters, okay? Now let me get my calculator back in the right mode. There we go. Now we're back in the right mode, okay? All right, so that's how you do that. That's pretty easy, isn't it? It's not bad. Now let's look at number 20. And it's on, I think, the same page. Yeah, so we're going to look now at number 20, page 513. Yeah. And it says we've got, I think this one's kind of long, too. Yeah. All right, so we've got a 1 kilogram block is attached to a spring with a spring constant of 16 newtons per meter. So we got a spring here, and we got a 1 kilogram block. The mass of the block is 1 kilogram. And the spring constant is what? 16 newtons per meter? Yeah, 16 newtons per meter. That's the spring constant. Okay. While the block is sitting at rest, a student hits it with a hammer and almost instantaneously gives it a speed of 40 centimeters per second. Okay. So then he hits it, all right, and so the velocity then becomes 40 centimeters per second, which is 0.4 meters per second. Okay. Okay. Now, so he hits it, and the spring compresses, doesn't it? And here we are, okay? All right? So he hits it and the spring compresses, right? What are let's see, what are, first of all, the amplitude of the subsequent oscillation? So we want to find, for A, we want to find what the amplitude is, right? We want to find what the amplitude is, okay? How in the world are we going to find that? Okay. Well, in actuality, this is a conservation of mechanical energy problem. Okay. All right, and so we look at what? What is conservation of mechanical energy? Well, it's K final, kinetic energy final, plus potential energy, and by the way, that's elastic potential energy. Final is equal to kinetic energy initial plus elastic potential energy initial, okay? All right, so let's write all this out, okay? Let's write all this out. Now let's think about let's write our equations out, okay? All right, and something else I want to do here. Well, no, everything's on the right side, okay. So that's going to be what? That's going to be 1/2 mv squared yeah, that's going to be 1/2 mv squared all right, let me double check something here. All right, hey, wait a minute, I got to pause a minute. If I ever get used to this. All right, sorry about that. Now, so before we go any further, let's determine what's positive and what's zero and what's not zero. Well, we know that kinetic energy is 1/2 mv squared, and elastic potential, there's actually a couple of different equations that we could use. But since we're looking for amplitude, elastic potential energy can be found by 1/2 K times the amplitude squared, okay? All right, now let's look at what's what's zero and what's not. All right. Well, we know there's a final kinetic energy. So initial kinetic energy at setting at rest is zero. Okay, right? And final potential energy is going to be what? Zero. So this term is gone and that term is gone. And so what are we left with? We are left with final and kinetic and initial potential, correct? All right, now let me think about that. Yes, okay. So we have basically this, 1/2 mv squared is equal to 1/2 k a squared. And we want to find k, don't we? Okay, well, the good thing about this, the 1/2s cancel out. So if you multiply both sides by 2, those cancel out. We want to solve for a, so we do what? We say a is equal to, all right, we divide both sides by, multiply both sides by 2, the 1/2s are gone, divide both sides by k, and so we have what? We have mv squared over k, right? Right? And then we do what? Then we take the square root of everything, both sides, and so a is equal to what? The square root of m over k, now watch out, times v. v is not another radical, right? Right. So then a is equal to the square root of, the mass was 1 kilogram, divided by 16 newtons per meter, times the velocity is 0.4 meters per second. Okay? And so we get an answer of what? The amplitude is what? So we got 1 divided by 16, so 1 divided by 16, and then take square root of that, times 0.4, and we should get 0.1. 0.1 meters or 10 centimeters. Now that's for part A. Okay, that's part A. Now what about part B, 20B, all right? Okay, it says, what are the block speed at the point where x is equal to 1/2 of A? Okay, so we've got to find it where, at the point where x is 1/2 of A, right? Okay, so basically what we're going to do then is we're going to plug this back into our equations. Really nothing changes as far as our equations. We're using the same equations. Now we're just looking at it in respect of x. And remember, x can be substituted for a squared. So if you take half of that, basically you wind up with this right here. And it says, what is the block speed? You wind up with this equation right here. Velocity, the final velocity, velocity 2 or velocity final. I always like to use F and I, velocity final, is equal to the square root of 3/4 times the initial velocity, okay? And you say, well, where do you get all that? Well, if you will go back to this equation right over here and plug it in, these equations I used, you'll see what I'm getting. If you'll go back and plug in for, instead of where it says A, put A over 2, and then work it out, you'll see where we get that, okay? All right, so we get the square root of 3/4 times the initial velocity, and so the final velocity then is equal to 3/4 times 0.4 meters per second. And you get an answer of 0.346 meters per second, or 34.6 centimeters per second, okay? Okay. All right. And you actually have to, I take that back, you actually have to use the entire equation, okay? You have to use initial and final on both sides. All right. But there you have it, okay? What was that, number 20? And then number 26. Let's go to number 26. All right. So we have a 507 gram mass oscillates with an amplitude of 10 centimeters. All right. On a spring whose spring constant is 20 newtons per meter. Okay. So this number, what was this, number 26? Yeah, number 26. So we got a 500 and, I guess we can do it this way. And the mass of the spring is 507 grams, which is 0.507 kilograms, okay? All right, oscillates with an amplitude of 10 centimeters. So it has an amplitude of 10 centimeters, which is 0.1 meters, okay? And it has a spring constant, a K constant, of what? 20 newtons per meter, okay? We need to find the period of the spring. We need to find the maximum speed and the total energy, okay? Well, this is really easy. To find the period of the spring, A, we use this equation right here. We say T, period, is equal to 2 pi times the square root of what? M over K. And so the period then is equal to 2 pi times the square root of the mass was 0.507, almost messed up, kilograms, over spring constant was 20 newtons per meter, and that is all under the radical. So 0.507 divided by 20, and then square root of that, times 2 times pi, and you should get 1. You should get 1 second, 1.000, 1 second, we're just going to say it right there, 1 second. All right, that's A. Now let's look at B. Okay. All right, B says the maximum speed, okay, the maximum speed. Well, basically what we're going to be able to say here is that K maximum should be equal to what? The elastic potential energy maximum, which is 1/2 mv squared is equal to 1/2 K A squared, right? All right, and so we got to do what then? We've got to find V max, right? Oh, shoot. Am I looking at the right? Yeah, I'm looking at the right problem here. Okay. All right, but since we are given the maximum speed, do we have to use these equations? No, we can actually go back to this equation right here. We can go back to this equation right here. All right. And we can say Vmax, I forgot about this one, we just used a minute ago. Vmax is equal to 2 pi F times A. So 2 pi, the frequency, times A. And you say, well, we don't have the frequency. Okay, we'll substitute 2 pi over T for that. So we'll say 2 pi F is what? F is 2 pi over T, right? Or excuse me, 2 pi times 1 over T, or 2 pi over T, times A, okay? So we got 2 pi, because the frequency is 1 over the period, okay, and there's your 1 over the period. 2 pi over the period, which was 1 second, all right, times the amplitude, which was 0.1 meters. And so we get a Vmax of what? We should get 0.628 meters per second. Okay. All right, now that is the Vmax, all right? Now, what about part C, 20C? Okay. And it says the total energy. Notice it says total energy. All right, well, total energy can be equal to what? The mechanical energy, right? So mechanical energy, E, is equal to what? 1/2 mv squared, right? And that's maximum, because it's velocity maximum. Because the maximum, look, you say, well, now, wait a minute, how can you do that? Well, because the maximum the maximum energy should be equal to the maximum potential energy. They should be equal to each other, okay? All right, so since we know the velocity, let's just do this. So in other words, it's actually the kinetic energy. And so we got 1/2 times what? Let's put that in kilograms, 0.507 kilograms times what? 0.628 meters per second squared. And what do we get? Well, let's see. We get 0.628 squared times 0.5 times 0.507. And I get 0.999, so I get 0.0999. In other words, it would be what? 0.1 joules, wouldn't it? Yeah, 0.1 joules. All right, and that's what you should be for part C. Okay, I hope this has been helpful.